Hey, thanks for joining me today, guys. We're going to talk about the remainder and factor theorems, and we're going to be using synthetic division to do our division, so we're not using long division. And we're just going to go over three really good sample questions that use synthetic division and apply either the remainder or the factor theorem. So we'll do the remainder theorem first. Remainder theorem says that we can find p of -2. So that's actually a question. The question is p of -2. The question is, what is p of x if you replace the x with a -2? And here we have p of x. P of x is 2x to the fourth minus 3x cubed plus 3x squared plus 1. And notice that there's a bunch of x's, it's a bunch of powers, and it's going to be kind of awkward to raise -1/2 to all those different powers and calculate that. But if we can use the remainder theorem, which says if we do synthetic division with the number that we're trying to evaluate, so -1/2 here as the thing we're dividing by, and then we'll do synthetic division, dividing that into our polynomial. So we're going to take all the coefficients of x's, starting with x to the fourth power. X to the fourth power, the coefficient is 2. X to the third power, the coefficient is -3. X to the second power, the 2 power, is +3. And then x to the first power, and notice there is no x to the first power here. It's missing. We skipped it. But we can't skip it when we're doing synthetic division or even long division. We have to put the coefficient in. The coefficient is 0. The number is 0 because there's 0x to the first powers. And then the coefficient of x to the 0 power, well, what is x to the 0 power? That's just 1. So x to the 0 power is the term without an x. And that is the constant term at the end there. That's the +1. So now I have my 1, 2, 3, 4, 5 coefficients, which is how many we should have in a fourth degree polynomial. And now we'll do our synthetic division. This isn't really about synthetic division, but you're going to get to see it being done. Remember that we add going down, and then we multiply going up. And the adding is just the column, so 2 plus nothing is 2. And the multiplication is the bottom number times the number in the little box there, so the -1/2. So -1/2 times 2 is -1. -3 plus -1 is -4. And then times -1/2, negative times a negative is positive. And 1/2 times 4 is 2. Half of 4 is 2. 3 plus 2 is 5. And now we'll multiply up. 5 times -1/2 is going to be negative. And that's just 5/2. Okay, 0 plus -5/2 is -5/2. And then -1/2 times -5/2 is +5/4. And this is really the first time that we've had any sort of trouble. I hope you've been able to follow the multiplication. Has been fairly easy. Times 1/2 is the same as divide by 2. 5 times 1/2 is 5/1 times 1/2, and we just multiply across to get 5/2. But now we're adding 1 to 5/2, and that one we have to think in our minds. We have to think about 1 is the same as 4/4. So 1 is 4/4 plus 5/4, and that is going to be 9/4. Okay, so in my opinion, that's probably the most difficult addition that we had to do, the most difficult addition, multiplication. And there we have it. That's the remainder. And the remainder theorem says that p of -1/2 is equal to just the remainder. Now, let me show you what that means. And we'll do it in green over here. let's do this problem the old-fashioned way. P of negative 1/2 is 2 times negative 1/2 to the 4th power minus 3 times negative 1/2 to the 3rd power plus 3 times negative 1/2 squared plus 1. And you can see that's pretty daunting. We can do it. Let's see. So negative 1/2 times negative 1/2 times negative 1/2 times negative 1/2. So there's 4 of them. 4 negatives multiplied together is going to be positive, so it's going to be positive. We just do 1 times 1 times 1 times 1, which is 1, and 2 times 2 times 2 times 2, that's 16. All right, now we'll do the negative minus 3, negative 1/2 cubed. That's an odd number, so this is going to be negative. 1 on top, 2 times 2 times 2 is 8 on the bottom. And plus 3, negative 1/2 squared in even numbers, so that's going to be a positive. 1/2 times 1/2 is 1/4. Then plus 1. Now I'm going to cheat a little bit here and just look ahead and say, well, I think I'm probably going to end up adding a bunch of fourths together, so I'm going to say 1 is 4/4. Okay. We wouldn't normally do that step at this early in the game. Okay, so 2 times 1/16 is 2/16, which is 1/8. Okay, so that's the first one. And then negative 3 times negative 1/8 is positive 3/8. And 3 times 1/4 is positive 3/4 plus 4/4. And now you can see I'm kind of setting this up so I can add the 1/8 plus the 3/8 together, and then I'm going to add the 3/4 and the 4/4 together. I'm hoping that this will all kind of come together in the end. So 1/8 plus 3/8 is 4/8, 4/8, and then 3/4 plus 4/4 is 7/4. Now it's tempting to turn that 4/8 into 1/2, which would be true, but I want to add it to the 7/4, which can't be reduced. So I'm going to reduce 4/8 to 2/4 plus 7/4, and finally that gives me 9/4. So you can see there was a lot of crazy multiplication of fractions and then addition of fractions, and it was pretty daunting here, whereas the synthetic division gave me the exact same answer with a very limited amount of multiplication and addition of true fractions. It was not nearly as difficult. So now I'm trying to make this an advertisement for the remainder theorem, but I do have to admit it doesn't always work out this way. You could have a problem where you're just doing some horrendous multiplication and addition of fractions, but chances are, if that's the case, then the old-fashioned way would be even worse. Okay, that's the remainder theorem, and now let's do the factor theorem. And the factor theorem says that if you do division, so if you take our polynomial here, and we have 1t to the 5th plus t to the 4th plus 4t plus 4, if we divide that by one of its factors, and we're testing to see if t plus the square root of 2 is a factor, then the remainder will be 0. Okay, right? And that's true in real life, right? In real life. That's true with regular numbers, right? 12 divided by 3 is 4, remainder 0. So we would say that 3 is a factor of 12. 12 divided by 5 is 2, remainder 2. And so we say that 5 is not a factor of 12. So the remainder theorem is just extending to polynomials what we already know we know with regular numbers. Okay, so now we're going to use the fact that we know how to do synthetic division to test do our long division. Instead of doing long division, we're just going to do synthetic division, and so that'll make this a little bit easier. So synthetic division, we take the thing we're dividing by, and if I want to divide by t plus the square root of 2, then I'm going to put in the little half box here the opposite of that number, so negative square root of 2. And then the coefficients of my function, t to the fifth, t to the fourth, 4t plus 4. Okay, so we've got some 1s and we've got some 4s, so t to the fifth, the coefficient is 1. T to the fourth, the coefficient is 1. But t cubed, t to the third power, the coefficient is 0. And t to the second power, it's also 0. Notice that there's 2 missing powers of t there. But then t to the first power, there's a 4. And t to the 0 power, there's also a 4. So this is a fifth power polynomial, which means we have 6 coefficients. Right? 1 for t to the fifth all the way down to t to the 0 power. All right, let's do our synthetic division. Add down, we get 1 times negative square root of 2. We get negative square root of 2. Add 1, we get 1 minus the square root of 2. Okay, now this is where it gets a little bit tricky, because now I'm going to multiply 1 minus the square root of 2 times negative square root of 2. So I'm going to do that off to the side, because I can't do that in my head very easily. I could easily get myself mixed up, I should say. So I'm going to distribute this. Negative square root of 2 times 1 is negative square root of 2. Negative square root of 2 times negative square root of 2 is positive square root of 2 squared, which is just 2. So that is 2 minus the square root of 2. And just reverse the order there. Instead of saying negative square root of 2 plus 2, I'm going to say 2 minus the square root of 2. Then we'll add that to 0. And we get 2 minus the square root of 2 again. Now I'm going to multiply that by negative square root of 2. 2 minus the square root of 2. So we'll distribute. We get negative 2 square root of 2. And then plus, negative times a negative is positive. Square root of 2 times square root of 2 is 2. So this is 2 minus 2 square root 2. We'll add 0. We get 2 minus 2 square root 2 again. And now I have to multiply it by the negative square root of 2 again. Negative square root 2 times 2 minus 2 square root 2. All right, distribute. Negative square root 2 times 2 is negative 2 square root 2. Negative square root 2 times negative 2 square root 2. Well, let's see. Negative times a negative is positive. Square root 2 times square root 2 is 2 times another 2. That's a 4. And so I have 4 minus 2 square root 2. Now we're going to add that to 4. Can I do that? Sure. 4 plus 4 is 8. So this is just 8 minus 2 square root 2. Okay. One more time. We have to multiply by negative square root 2. So this is kind of what I was talking about, how sometimes these can be quite ugly. And we're going to distribute. Negative square root 2 times 8 is negative 8 square root 2. Negative square root 2 times negative 2 square root 2. Let's see, negative times a negative is positive. Square root 2 times square root 2 is 2 times the other 2 is 4. So we have 4 minus 8 square root 2. And then we're going to add 4 to that. 4 plus 4 is 8 minus 8 square root 2. The remainder is 8 minus 8 square root 2. Now you can see there's quite a strong pattern showing here in the code, the numbers that are left over. 1 minus the square root of 2, 2 minus the square root of 2, 2 minus 2 square root of 2, 8 minus 2 square root of 2, 8 minus 8 square root of 2. So you can kind of see some sort of a pattern developing there. We could maybe imagine, maybe this isn't a very good example, we could imagine how this could have ended up with the, with the whole number canceling out, right? If this had been a minus 4, right here. Let's see, if this had been a minus 4 plus 4 would be 0 minus 2 square root 2. And so we could imagine that this would have ended up with just, if we'd ended up with just a negative 2 square root 2 there, then when we multiplied by the square root of 2, that square root would have canceled out and we're left with just 4. And if this had been a minus 4 and we had been left with just a 4 here, then we would have had a 0. So actually we can see that if it had been minus 4t minus 4, that t plus the square root of 2 would have been a factor. So this is certainly possible just because the answer is no, not a factor. I don't want you to get the idea that, well, just because it was complicated and there was a square root involved, that's why it wasn't a factor. No, that square root could have very well been a factor if there had just been two small sign changes in our polynomial. Okay, so that's how we do this. We do synthetic division. Hopefully you don't end up with a really complicated square root as the thing we're dividing by. But even if we do, we can do synthetic division. And then if the remainder is the last one under the constant coefficient, right, the 4 there, if that last remainder is 0, then it is a factor. And if it's not, then it's not a factor. And let me just say one real quick statement about this. So when you have a polynomial, polynomial is made up of factors. In this case, it would be t, right? T minus r times t minus r. Let's just call them r1 and r2. And it's a fifth power, so this can be t minus r3 and t minus r4 and t minus r5. So there's going to be 5 factors, potentially 5 factors. And so the factors, when we say the factors are going to be t, the variable, minus some number. That's the factor. That number is called a root. So when we solve a polynomial and we find its roots, then that is the number that we put here. So the numbers that go here in the synthetic division are called roots, and when we put them into a binomial t minus a root, that's called a factor. And notice that the root has the opposite sign of what you see when you look at the factors. So that's just an observation to make, that there is a relationship between the roots and the factors, but there's a change in sign that goes on there. So that's something to watch out for. Okay, last question. Solve the given that one root is negative 4. Okay, so now we have an equation. We're not looking for the factors. We're looking for the roots. We're looking to solve this one. Later on in future lessons, we're going to talk about how do you come up with the potential roots, like how do you know what numbers might be roots or what numbers to try here. But in this problem, we're just going to give you the first root, and the first root is negative 4. So we're going to divide by negative 4. What we're actually dividing by is t minus negative 4. So we're dividing by t minus negative 4, or t plus 4. And we're saying, is that a root? Now, of course, we don't need to find out if it's a root because we're told that this is a root. But we're going to see that if we do long division, we can get some useful information here. So the coefficient of the first t cubed, is 1. Coefficient of t squared, well, there is no t squared, so it's going to be 0. And t to the first power, negative 11. And then t to the 0 power, that's 20. Okay, so we're just doing long division. We should be really good at this by now. Add 1, multiply by negative 4. Add down, negative 4. Multiply by negative 4, we get 16. Add down, and we get, let's see, what is that? That's 5. Multiply by negative 4, we get negative 20. Add down, we get 0, which is what we expected, right? We knew that. We proved that negative 4 is a root. So let's have a list of the roots. The roots are, and there's going to be 3 of them, but one of them is negative 4. And now we need to find the other 2. And then we can have a list of the factors. And the first factor is t plus 4, t minus negative 4. And then there's going to be two more, t minus something else, and then t minus something else. So there's three factors of this polynomial. There's three roots of this equation when the polynomial is equal to 0. And that's what we're looking for. Okay, now here's the big excitement for this problem. How are we going to find the other roots? And what we have down here is we have the remainder was 0, which means that we have 1x, or I'm sorry, it's not x. Oh, bad mistake. We have 1t squared, 1 less than the t cubed, minus 4t plus 5t to the 0 power, so t to the second, first, 0. That's the answer to the long division or the synthetic division when we divide t cubed minus 11t plus 20 by t plus 4. And so that is also a factor, and if we can factor this further, or we can solve this equation, t squared minus 4t plus 5 equals 0, we can find the rest of the roots. And of course, this is a quadratic, so we don't have to do anything fancy. We can just do the quadratic formula, and that's what we're going to do. And so we're going to say that a is 1, b is negative 4, and c is 5, and we'll apply the quadratic formula. Notice that a is 1 was the first number I got there, b negative 4 is the second number, and c 5 is the third number, and then the remainder was the last number. So when we end up with a remainder of 0 and then the last three digits, that's when we turn to the quadratic formula. We stop trying to use synthetic division. Okay, so let's do this real quick. X equals negative b, negative 4, plus or minus the square root of b squared, 16. Negative 4 squared is 16, plus or minus 4ac, so minus 4 times 1 times 5 is 20, over 2a, 2 times a is 2. 16 minus 20 is negative 4, so we end up with 4 plus or minus the square root of negative 4 all over 2. Well, that's 4 plus or minus 2i. The square root of negative 4 is 2i divided by 2, and that is going to be 2 plus or minus I. 2 plus or minus I. Now, notice that that is actually two answers. That is 2 plus I and 2 minus I. So we could say this is t minus 2 plus I and t minus 2 minus I. So those are my three roots if the question had asked for the roots. Those are my three factors if the question asked for the factors. And this is how we use synthetic in combination with the quadratic formula to find all of the roots of a polynomial function. Thank you very much for watching.